Ayu. Oh shit, masih CCTV dia kena buka.
Now.
Apa?
Betul. Kat sini lah. Apa benda? Bukan apa benda. Daripada table
Kata.
ada bagi.
Dah taruh tu bagi.
Bawah. Ada lagi bawah. Kau kena scroll sampai bawah sekali.
Mampu dah ke? Okay. Mampu dah ke? Okay.
Betul lah yang second ni.
Plot.
Plot. Oh, haa. Betul. Jaga aja aku buat balik.
Plot apa ni?
Plot apa ni?
Second graph aku lupa nak tu. Oh, scan lah.
Ya. Oh, kau maki terus. Tak tally dengan table.
Tak, sebab aku lupa nak tukar. Sebab kita kan tukar data. Aku lupa nak apa hal gambar kau scan je. Kau belum.
Oh, yang
Ada kat
equation
tepi.
semua tu
Aku lupa nak tukar pula.
Maksud kau yang lain? Macam screenshot. Apa kita screenshot?
Apa benda screenshot Azri tu je. Kan kita ada tukar data.
Good morning. Assalamualaikum warahmatullahi
Boleh yang
wabarakatuh.
actually data
Hope
kita
you guys
pakai
are
yang
fine.
lain. Lepas tu kita tukar.
Can you hear me?
Can hear, Doctor.
Thank you. The QR code is now being shared. So I will start a moment. I now to record lecture, but my spin wheel is spinning. Today we will start looking at fractional distillation using enthalpy concentration method. I haven't uploaded the notes yet, but I will do it by today, inshallah. We are done with mercaptil, but before I leave mercaptil, I would like to point out the mistake I did during the last lecture. In the meantime, whoever just joined us, please scan the QR code. last lecture, we were looking at how to get the number of stages when the free efficiency is given. I'm not sure why is my iPad not now. Why it's not connecting? Try again. This is strange. What's happening? Why is not connecting? I cannot conduct my lecture if my iPad shared with you guys. What is going on? Yet. Well, this never happened like this. Hold on. It seems to be something wrong. This is weird. Why is my iPad not being shared? I have no problem last week. What happening now? This is terrible.
Doktor tak.
Okay, sorry, I forgot to unmute. Okay, guys, we're going to look at enthalpy concentration method. When you're looking at McCarthy method previously, the assumption in order to use McCarthy method is that it has to have equal molar flow rates, or another way of another term for it is molar overflow rates. They should be equal. Meaning, if you're looking at the enriching section, the liquid flow rate will be the same throughout the whole enriching section, and the vapor flow rate will be the same throughout the enriching section. And if you are in the stripping section, your liquid flow rate will be the same throughout that section, and the same goes for the vapor. It should be the same in the stripping section. The flow rate should be the same, but you can only assume that if your latent heat for both components, they are the same. Okay? If the latent heat for both components, A and B, they are the same, then you can assume equal molar or molar overflow rates are the same. But not all components have the same latent heat. So you cannot always use McCarthy method. So in order to solve that problem, you'll be looking at it using the enthalpy concentration method. Okay, when you use enthalpy concentration method, you don't need to assume equal molar flow rates or molar overflow rates. You don't have to assume that. You will be taking into account the latent heat, the heat of the solution, and the sensible heat. So in this method, you have to do the material and the energy balance. You have to solve it simultaneously. Okay? And from when you do the enthalpy concentration method, you'll be able to calculate the reboiler duty and the condenser duty. So you'll be able to get the amount of energy for the condenser and the reboiler. Unfortunately, this method is using trial and error method. And your enriching lines and your stripping, the operating lines for the enriching and the stripping operating line, they are not straight, they are curved. That's the difference. They are not straight, they are curved. Because of the fact that they are curved, you need lots of points. You don't need only just 2 points to connect to get a straight line. Now it's a curve, so you need more points, and the method is by trial and error. Okay, so when so far we have been looking at binary mixture whereby you have component A and B. So when you do the enthalpy concentration method, you will use a reference state whereby the reference state is going to be the boiling point of component A, which is the lower boiling point component. Okay, you will choose your reference state to be the boiling point of component A, which is the lower boiling point component. So that's the things that we will be looking at when you apply enthalpy concentration method. So before we can use that method to solve for the number of stages, we need to get our enthalpies. Okay, so this is already plotted here, or you can tabulate it first and then after that you plot it. Okay, so this is the table for the enthalpy concentration data. And how to get the values of your enthalpy, you have the two equations over here. Okay, your small h or lowercase h is for the liquid, and the capital H is for the vapor. Now we are looking at saturated. Saturated means it is at the dew point or at the boiling point. So if you're looking at liquid, that will be at the boiling point or bubble point. If you're looking at gas or vapor, then that will be at the dew point. So this temperature is the temperature for the vapor, that is the dew point, and then this temperature is the temperature of the boiling point of your liquid. Okay, so you calculated it by using your T subscript 0 as the reference temperature, which we already mentioned happened to be the boiling point of the component A, which is the lower boiling point. Lower boiling component. Yeah. Your CPA is the heat capacity of component A. CPB is the heat capacity of component B. So where is CPA? This is CPLA, and this is CP CPYA. What's the difference? This is for liquid because that's where the liquid, the subscript L stands for, denoted liquid. The CPV, sorry, V, there's a V there. That means it is for vapor. So there's two CPA. Okay, one of it is for the liquid. That's the liquid, subscript L. And CPV, that's for the vapor. And if you're looking at component B, so this is for liquid B, and this is vapor B. Okay, so this value should be supplied for you to calculate the enthalpies. And there's another thing that I need to, this is the heat of mixing or heat of solution, and it should be at the reference temperature. Okay, normally you ignore that because it is negligible. So the heat of solution, normally you ignore. For hydrocarbon, it is very, very little, so you just ignore it. Okay, now this is latent heat. Okay, this is latent heat. If it's subscript A, then it's for component A. Subscript B, then it is for component B. But your latent heat here is calculated at the reference temperature TO. And for over here, you have the latent heat too, but that is at the normal boiling point. Okay, so your normal boiling point will have the latent heat at the normal boiling point will be having a subscript B, small lowercase b, small letter b. Okay, the one that has no subscript B is at the reference temperature. So I can't do the calculation. You have to look at the example 1161 in your textbook in order to see how the calculation is done, because I cannot share with you guys this morning. Somehow I'm having difficulty sharing with you guys my iPad, so I cannot calculate. Right? So let me show you guys the result from the calculation, and this is the tabulated result. Okay? So if you're looking at mole fraction, then your enthalpy will be kilojoules per kilomole. So if you're looking at mass fraction, then your enthalpy will be kilojoules per kilogram. So it depends on what you're using, mole fraction or mass fraction. So for distillation, normally we use mole fraction. So for the liquid, oh dear, I can't seem to be. Okay, this is for the liquid. I keep on highlighting the whole thing. Doing very well here. That's the reason why I prefer my iPad a lot. I just cannot do anything much using my computer screen. Okay, if you're looking at the enthalpy of the liquid, then it's the two columns on the left-hand side, whereby you have the mole fraction XA, that is for the liquid. So your enthalpy will be, should be small h, but it's written capital H subscript X over here. And the two column on the left, the right-hand side is for the vapor, saturated vapor. So it's already mentioned here, saturated vapor and saturated liquid. So you know that what you're dealing with. So if it is saturated vapor, if you look at the graph here, saturated vapor, that will be the line at the top. Okay, that's the line at the top here. And if you're looking at saturated liquid, it will be the line at the bottom. So the small h is for the saturated liquid, the capital H is for the saturated vapor. And if you look at it, it looks as if the two lines, they are parallel to each other. It looks as if it is almost straight. Okay, so this graph is the enthalpy of your mixture of benzene, toluene versus the mole fraction of benzene, only benzene. So why is there a subscript Y and X at the x-axis? If you are referring to the gas, you'll be looking at Y. If you're referring to the liquid, you'll be referring to X. So you have small h versus XA or capital H versus YA. So it depends on whether you are looking at liquid or vapor. So this is the enthalpy concentration diagram, which you will be using in order to get the enthalpies of your mixture. Yeah. How do you get this graph, or how do you get the table, the values in the table? You use these four equations over here. Yeah, so you can have a look at example 1161 in order to get the feel of how it's done. Yeah, any questions so far? I do apologize. I just don't know what's happened. I just can't get to share with you guys my iPad. If I have my iPad, inshallah, I'll be able to calculate and I'll be able to show you guys the calculation. But right now, I just cannot. I just can't, due to the fact that I cannot share my iPad with you guys. Okay, so these are the values that you get or you obtain after you have done the calculation at different values of mole fraction for gas and liquid, for vapor and liquid. Okay, now when we want to do I'm going to go straight to what we want, what actually is what we're going to do. Okay, this is how it's supposed to look like. Let me zoom in. Okay, this is what you guys going to do. It still look like as if it is mercantile. The only difference is that your operating lines, in this case, it look like it's as if it is straight, but it's supposed to be a curve. Okay, the broken line here is the straight line. The straight line which we assume equal molar overflow or constant molar overflow. Okay, the straight line, the dotted line is straight. This is the one that we have done using the mercantile method. The solid line here is the line that you obtain using the enthalpy concentration method. It's not straight. It looks almost straight because of the fact that benzene and toluene, the latent heat is almost the same, but it's not. Okay, so that's why it looks almost straight, but it is not straight. Your Q line will be still the same. It's still the same method that you use to get your mercantile method. It's still the same. But the only difference is that now the operating line for the enriching and the stripping is no longer straight. You cannot just get one point at XW and another point at the intersection of the enriching and the Q line. You cannot just draw a straight line. It's no longer straight. Okay, so this is what we're supposed to do. Once you manage to get your operating lines, which is curved, then you'll be able to do the steps. Then the number of steps that you obtain will be the number of stages that you need for the distillation. Okay, so let's start. Let's look at how it's going to be done. This is the example from example 1141, if I'm not mistaken. Okay, because it is by trial and error method, so we have the procedure here. Okay, so this is for the enriching operating line. So over here we have our column. We have our condenser, which will have a QR there. The QC. QC is subscript C is condenser. Capital R is for reboiler. Okay, so you need to find, using the material balance here and the energy balance here, you solve it simultaneously, then you will be able to get the operating line. So first of all, based on the reflux ratio given, you should be able to calculate V1. I can seem to be able to, I need to have my, okay. You should be able to calculate V1 based on L once you are, the reflux ratio is given. From the previous calculation, the material balance that you have done, you already managed to get D. The distillate flow rate you already managed to get. So R is equals to, let me try to write, R is equals to L over D. Not a good, not a good handwritten, not a good. Okay, let's just bear with it. Okay, that's your reflux ratio is equals to the liquid flow rate divided by the distillate flow rate. So if you already know what is your distillate flow rate, you should be able to calculate your liquid flow rate. And if you know what is your liquid flow rate, and you know what is your distillate flow rate, that means you'll be able to calculate your vapor flow rate, V1. Okay? Okay, you should be able to do that. And you will choose one value of x. One value of x, anything between xd and xf. Okay, if you already know what is v1, then you will know what is vn plus 1 because this will be v1. If you already know what is L, then you will know what is Ln. So over here you have Vn plus 1. Over here you have Ln. So you should be able to use this equation to solve for Yn plus 1. That's the Yn plus 1. Okay. Once you manage to solve for Yn plus 1, you will need to calculate Vn plus 1. How to calculate Vn? This is the one that when you assume constant over when you assume constant overflow, this is an assumption because this is your first assumption. This is your first trial. Okay. So based on that value of y1 plus n plus 1, calculate h, the enthalpy n plus 1. And how do you calculate the enthalpy n plus 1? You will use the equation, you will use the equation for the saturated vapor, which is that equation, this equation. You will use that equation. You already know what is your yn plus 1. The rest you can, the value of the rest of the variables, you can get it from the solution, from the equation, except for the boiling point of your vapor. The boiling point of your vapor, you can get it from the temperature versus concentration, the diagram of the temperature versus concentration. Or you can get it, I'm not sure whether you can get it over here because there's no temperature over here. There's a diagram for temperature versus concentration. So you should be able to get the temperature of your mixture from the diagram, which is, if I'm not mistaken, figure 11. At the very beginning of our lecture, we have that diagram, okay, when we were talking about Mercalli method. So you have that temperature versus concentration diagram. So you should be able to get the temperature of your mixture at the composition YA. You should be able to get that temperature. So, and then you'll be able to calculate your enthalpy. And from that enthalpy, you have this value now. Okay, you have that value now based on the value you calculated from the material balance. So now you have this enthalpy. You can calculate the enthalpy of HD because you already know the composition of XD using the equation for the liquid enthalpy. You can use this equation. You can ignore the latent heat of solution. You can get the boiling point of your or the top temperature of your column. You can get that temperature again from the temperature versus concentration because you already know what is the mole fraction of your distillate, which is XD. Okay, so you should be able to calculate HD now. So now substitute it into this equation. You have that HD there. Okay? And you can calculate H1. Where is H1? Because you assume that Y1. Okay, now I need my point. Okay, your Y1 here. Oh dear, very difficult doing this lecture using the computer. Y1 is here. Okay, Y1 is going to be the same as XD. It's the same value. So from this value of XD, you should be able to calculate H1, but don't use the small letter, the enthalpy for the liquid, but use the enthalpy for the calculation for the vapor. Okay, so let me go back to the equation. Instead, just now you calculate HD using this equation. Now you're going to calculate H1, capital H1 using this equation. Because this value, YA is going to be the same as Y1 is going to be the same as XD. This is quite difficult, isn't it? Following a lecture like this. Anyway, you already managed to get that. Okay. Hn. Where is Hn? Is the value that you get from this value x. From that x is the one that you will use to calculate Hn. This is the x that you choose for yourself. You will calculate Hn. You substitute the x inside this equation. Small h here, that's the x. You will calculate your small h here. So once you manage to do that, you will have enough information to recalculate Vn plus 1. To recalculate. Okay. Now you have to solve for Vn plus 1 from the energy balance. Okay. So when you manage to do that, Vn plus 1, you should be able to do the material balance, use the material balance, or use this equation to calculate Ln. Okay, calculate Ln using don't use the equation yet. Use your material balance. Use your material balance. This is Ln. The bottom part is Ln. Hold on, I need my pointer. Okay, your Ln is here. You managed to get your Vn plus 1. Okay, your D, you already know. So if you do the material balance, Vn plus 1 you already managed to get. Your D is already solved for, so you should be able to solve for your Ln. Okay, so that's the number 5 solution. Once you manage to get Ln, you substitute it over here. From the step number 4, you already managed to get this. Okay, you managed to get your Vn plus 1. Your D is the value that you initially calculated based on the material balance earlier. So you should be able to recalculate that value now. Initially, you get that value by assuming a constant molar overflow. You get that value from number 3. Now, for number 6, you recalculate it again using this equation. And now you have to compare the two of them from number 3 and number 6. This is the try and error method. You compare step number 3 with the answer, the value that you got from step 3 and the value that you got from step 6. If it is the same, then you proceed to calculate step number 8. Meaning you choose another x value. Okay, so if it's the same, then this is your x coordinate, and this is your y coordinate. That's your first point. Because you need points in order to plot your operating line. So your first point will be the x that you selected earlier, and the yn plus 1 that you recalculate. But if it's not the same, if your calculated value of yn plus 1 from part 3 and step 6 is not the same, then you have to go back to step number 3 by putting these new values into step number 3 and redo everything all over again. But normally, one iterative is enough. You just do it once and it will converge. Okay, so once you manage to get your first coordinates, x and y, then you repeat the whole step all over again for another point, which is for another x value. So any questions? It's a try and error method. Any questions? Quite confusing?
For the enricher operating line, is it still a straight line or?
It's no longer a straight line. It's a curve.
Oh.
Somehow for the diagram shown here, the diagram shown that I showed earlier, for the diagram, it looked like it's a straight line, but it's not. Okay, it is slightly curved. The reason why it looked like a straight line is because the latent heat is about almost the same. This is not a good example because, okay, if you look here, the latent heat in the last column, the latent heat is about almost the same. That's the reason why the line look almost straight. but actually it's not. So the data that you need in order to calculate the enthalpy, here you have the CP for your liquid and your vapor. This is the latent heat for its normal boiling point at this boiling point, at the boiling point of benzene and toluene. So the last column is the rightmost hand side column is for the latent heat at the boiling point. Okay? So that's the latent heat at the boiling point. And the CP for liquid and vapor is given here. So these are the values that you're going to use if in the equation that we were looking at earlier, and this equation. Okay. So this is the latent heat that is calculated from these two equations. Okay, this is the latent heat calculated from the top equation. This is the latent heat calculated from the bottom equation. But the latent heat at the boiling point, where is the latent heat at the boiling point? Okay, this is, I need my pointer again. The latent heat at the boiling point is here. That is the latent heat of component A, for our case, benzene, at its boiling point. And this is the latent heat of toluene at its boiling point, which is given in that table earlier that we just look at on the most right hand column of the table. That's the value. Okay, but this value you have to calculate using the equation. So this is where you will substitute it here. Okay, and for this value, you will substitute it over here. You need to calculate it using this equation. Okay, the CP just now, that's for the gas of the vapor of B. And this is the CP of, what's the difference here? This is liquid, sorry, this is for liquid. This is for liquid, this is for gas, vapor, sorry. Yeah, this is for liquid. And this is with the subscript Y, is for your vapor. So that's the two different CP denoted by Y for vapor, and without any subscript Y, that's for the liquid. So this is another way of looking at it. This is for liquid. And where is the vapor? This is the vapor. This is another way of writing. Is somehow, I must have got this from equation from a different source. That's why there's no consistency in the nomenclature. Any other questions? So what you have to do, let me go back to the graph. You have to get a few points in order to draw your curve operating line. So your operating line is actually this line. I'm not doing a good job here. That's the line, not the broken line. The broken line is for a straight line. Okay, so let me undo this. Is there any way I can undo it? Yes, that's it. Okay, so you're supposed to get few points. For example, 1 point there. Okay, 1 point here. Maybe 2 of it. Obviously, you know you're going to need that point there at XD. So you need only maybe 2 points. You get your curve. After that, you repeat for the stripping line. You have 1 point at the XW. Okay, you will need another 2 points in order to get your straight line. Not straight line, sorry, your curve operating line. So for your stripping section, you will also do it by trial and error method, but obviously the material balance and the energy balance will be different. Okay, so your Q line, for your Q line, is still the same. You use the same method as what we have done for MyCap and TIL. It doesn't differ. Okay, it's still the same. Let me go back to the notes on the stripping operating line. Okay, this is for the stripping operating line. You have this, okay, this is the stripping operating line. Oh dear, why can't I highlight the whole thing? This is your stripping operating line. Again, you have to find the LM, VM plus 1 as what you have done for the enriching section. Okay? Your W, obviously, you already know that from the metal balance calculated at the very beginning of the problem. So you already know that. Okay, so it again is a trial and error method. Once you manage to do that, you check your calculated value from the earlier calculated and then the new calculated value. If it's the same, then you got your pay for the X that you assume. Again, you have to assume an X. You assume an X which is between XW and XF, because this stripping section is from this XF to the value of XW. So your X must be between these 2 points. So whatever X you choose, after that you do the same thing as what we have done, just like similar as what we have done for the enriching section. We will do the same thing for the stripping section and recalculate your X, your Y. Okay, recalculate your Y and check it with the earlier calculated value and the new calculated value. If it's the same, then you already have your pair, which is the coordinate X and Y for your first point. And before you can do that, you need to let me see. You need to get your condenser duty first. You need to calculate your condenser duty. You need to get your condenser duty. And when you have done your enough points to get your operating stripping line, you can calculate your reboiler duty. So this is quite a long method. It's quite a long method. So, and it involves trial and error. Even though the iteration sometimes is only once, you don't have to do a lot of iterative calculation, but still you need at least 4 points. Okay, 4 points, 2 points for the sweeping and 2 points for the or 2 coordinates for the sweeping and 2 coordinates for the enriching, in order to have enough points or coordinate for you to draw your curve operating line. So you will repeat the same procedure for the stripping section, just like what we have done for the enriching section. You will still do the same thing. And after you have got your operating line done or drawn, then you'll be looking at the stepping of the number of stages. And these are the steps given, how you're supposed to get it done. Okay. And the final graph will look something like this. So again, compare with the previous McCarthy method and the enthalpy concentration method, the answer is quite a bit different. If you look at the solutions from the textbook, if you use the McCarthy method, whereby you assume equal molar overflow rates or equal molar flow rates, you get 9.9 stages. But if you use this enthalpy concentration method, the answer is more than that. It's about 10.4. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10.4. So there's an extra of 1.4. Oh, sorry, about an extra 1 pages because of the not assuming constant equimolar flow rates. When you do not assume constant molar flow rate, which is the actual case in this example, you get 1 extra stages more. Because initially it was only 9.9. Now you got 10.4. So it's an extra stage. Due to the fact that the enthalpy of benzene and toluene, not the enthalpy, the latent heat of benzene and toluene, they are not the same. Okay, so let me point that out. Let me use my, okay, there you go. This is the latent heat of benzene, and obviously it's not the same as that of toluene. There's a slight difference there. So if due to the slight difference, so the operating lines still almost look straight because of the small difference in the latent heat, because it's quite close. So your operating lines for the enriching and the stripping, they are almost the same. Almost, I mean, it's not almost the same. They are almost a straight line, almost straight line. It look like a straight line, but it is actually slightly curved. And in fact, the operating lines, they are above the initial operating line using McCaptil method. The broken line is the one that is using McCaptil method. The solid line is the one that we just got using enthalpy concentration method. So any questions? You can have a look at the example 1162, get an idea of how it's supposed to be done. But unfortunately, this method is only for a binary mixture. That means you have only two components. You cannot do it for multi-component. This method is more realistic compared to McCaptil, because McCaptil assume that the latent heat for both components are the same, which is not always the case. But McCaptil is easy. The method to use McCaptil is easy. So you have, so that you can, if something is almost the same, the latent heat is almost the same, that the difference in the number of stages is not that much if you are using enthalpy concentration method, as we have looked at this example. Any questions? Any questions? I will upload the notes in e-learning by today. Okay, so as you can see, the solution is pretty long. Okay, how many pages? How many slides? It's pretty long. So I'm just mentioning it, the procedure on how to go about it, the procedure. But there's how many slides? I say that's a long one. That's a very long solution. Any questions? No questions? Okay, if there's no question, we'll stop here. I will hopefully try to solve what is the problem with my connection, why I can't share my iPad with you guys this morning. Alhamdulillah, I managed to cover this topic for the time. Oh, QR code, you wanted it. Okay. Hold on, I need to find where is my... Since there's no question, I think we stop here. For those that haven't scanned the QR code, okay, I'm sharing it now. Okay. Your test 2 is going to be on the 19th of January. That's about a month from today. Okay, welcome. And you will be looking at McCaptil only. Okay, so you will not be tested on this enthalpy concentration method. Obviously, it's not practical to do that because it's an try and error method. Is it will consume too much of the time. And there's another, you will not be asked on multi-component distillation, but I will proceed to cover it after this because you have your project that you need to do. So I will ask you to we will be looking at the shortcut method. We will not be looking at the rigorous method. The rigorous method is the most accurate, but we will be looking at the shortcut method. The shortcut method is just an approximate method. So I want you guys to solve your project using the shortcut method. It's just an approximate method. You will do the rigorous method when you do your plant design. Right? So just for this project, for this subject, just do the shortcut method, which we will cover in multi-component distillation. Inshallah, by this Thursday, we will start looking at multi-component distillation. I will still need to cover it because of the project. Initially, I thought I want to do it at the very end of the semester, but you still need to do your project. Okay, guys. Any questions before we end the session? No? Okay, thank you very much. So sorry about the hiccup earlier. Hope by Thursday everything goes smoothly for our lecture. Okay, Assalamualaikum warahmatullahi wabarakatuh. And thank you very much.
Thank you.
Thank you, Doctor. Thank you, Doctor.